Good morning, all of you. So, in today's class, we will learn some applications of elastic behavior of materials. So, see, when we are constructing bridge or a building, we are giving particular shape to the columns or beams which we are going to use. Why we are giving that particular shape? That is also having a reason. Even you might have seen cranes are there which we are using to lift vehicles. There is a wire, so that wire is not like a rod. Okay, that wire is not just rod. It consists of small wires, steel wires, and bunch of that is nothing but the wire which we are going to use to lift the vehicles. By wire only. That is also having one reason, right? So let's see in detail what is that reason and why we should give that particular shape. The first one, that is in bridge and buildings. So bridge is bridge is so designed that apart from its weight, apart from its weight, it should be able to withstand, it should be able to withstand number one is what is going to affect, that is what we can say traffic, you know? That is load of the traffic, load of the traffic it should be here. And next one, again what is there, wind. So the force of wind, force of wind, these two things or these two it should bear. So now how to make columns so that it should bear the load? See here some examples I am giving how we are going to use. So suppose now this is a column or beam, and now we are hanging some weight. This I am denoting with the dotted line. This is initial position we can say. And when we are hanging the load, what happens? Let's see. Yes, something like this. And we are hanging load somewhere here. Right, like this. And this is what its depth we can say. This is its length, and this is load, that is W. And from this center of mass to this center of mass, whatever deviation we are getting, that is delta. Right? And actually, if we will see, something like this beam will be. This is what is I'm giving this, something like this, right? And for this column, this is depth D, and this is breadth. Okay. So if you want to find this depth, or what you can say shift displacement, then this D is or delta is equal to W L cube divided by 4 B D cube into Y. L is what? Length of this. W is load. B is this breadth. D is this depth. And Y is Young's modulus. So from this, I can write like this, that is delta is direct proportional to length. Second one means more the length, more will be the elongation or shift we can say. Next, delta is direct proportional to 1 by B. So breadth is more, this displacement will be less. And third one, delta is direct proportional to D cube. Y is obviously there, but it is constant. So by use of same material, we can make some width or breadth or this length. And from that, if you want more or less according to that, you can use the material. Understand? So we should think about this to use the material of how much width or how much depth or how much breadth we have to use for constructing according to our requirements. Understand? This is what bridge and buildings. Okay, right. Note down. Right, finished. Next. Now another example or application we can say, that is crane. What is that? Crane. So what we are doing in this, see, as I already told, we are using one wire, that is bunch of wires of steel. You know why we are using that? That is what the reason. See here. First, I will tell you something. See, here it is a crane. Okay, this block is something like a crane. Okay, and here there will be one pulley. Okay, there will be one pulley, and this wire will be there. This wire, and now at this wire you will have something like this hook. Have you seen? Like this hook will be there. And now suppose this is the vehicle which we want to lift. Okay, right? Something like this broken vehicle. This is like this. So this, whatever this wire is there, this wire is bunch of small wires, है ना? Right? Why is it so? Let's see. Understood? Okay. So why is it so? Let's see now. So now suppose if A is the cross-sectional area of a crane required to lift load mg, then stress in crane is equal to load by area mg by A. So Sy, that is yield strength should be greater than the stress and the stress, that is Sy should be greater than or equal to mg by A, or A should be greater than or equal to mg by Sy. Then only it will withstand, otherwise it is not possible. Otherwise the wire will get permanently deformed. है ना? So this otherwise permanent deformation of rope. Keep it in mind. Or you can write like this also, to avoid permanent deformation of rope. है ना? Can you write like this? To avoid permanent deformation of rope. To avoid permanent deformation of rope. Understand? So this we have to take it into consideration. Now one example I am telling. Suppose I want to lift load of 10 metric tons. 10 metric ton. That is equal to how much? 10 into 10 to the power 3 kg. 10 into 10 to the power 3 kg. And rope is made up of steel. Rope is made up of steel, suppose. That is Sy they have given something 3 into 10 to the power 8 Newton per meter square. Then I want to find area. How much area you should get? A should be greater than or equal to mg by Sy. So mg how much we are having? 10 into 10 to the power 3 divided by Sy how much? 3 into 10 to the power 8. So this is equal to how much? 3.3 into 10 to the power minus 4. है Yes. G also there na? G also there. So this is 10 10 to the power 3. One more 10 we should get because this G is here. So 3.3 into 10 to the power minus 4 meter square. That is equal to 3.3 centimeter square. So this much area of that rope should be there to withstand equal to or greater than karo, right? Equal to or greater than this much area should be there. Understand? So why single wire is not used, that I am going to tell now. If we have used this 3.3 centimeter square, but for safety purpose, for safety we'll use 3.3 into 10, that is equal to 33 centimeter square rope. Area rope for safety, 10 times of that, so that it can bear 10 times of that load also, for safety purpose, because sometimes it will get stuck into some mud or something like that, so many stones or whatever it may be. So for that we are using this type of thing. So if now you are having area is equal to pi r square, which is equal to 33 centimeter square, and from this if you have calculated this r, then r you are getting equal to 3 centimeter. Yes, how much you are getting? 3 centimeter, nearly equal to, if we will calculate. So but single wire of 3 centimeter, note down this, but single wire of 3 centimeter would not be flexible, would not be flexible as it is rigid rod, as it is rigid rod, and therefore ropes of cranes, therefore ropes of cranes are made by number of thin wires, are made by number of thin wires number of thin wires woven together into a rope of required radius. Required radius. Ropes of cranes are made by number of thin wires woven together into a rope of required radius. This is what the reason why we are not going to use single wire. Understand? Yes. If you want this previous slide, just see this and note down. Pause the video and note down this. And here it is, next one. Okay. Now next. That is third number application, we can say. Maximum height of a mountain on earth. Maximum height of mountains on earth. maximum height of mountains on earth. Okay, so how much it should be, right? So see, rocks will have elastic properties, so we have to consider it. If h is the maximum height of mountain, if h is maximum height of mountain, maximum height of mountain, this is like this, it will be mountain, है ना? Right? So this is the base, and rho is average density. Rho is average density of its material. Everything in that soil, rock, whatever, of its material. Then stress at bottom, stress at bottom of the rock is equal to H rho G. H rho G, right? Okay. So now yield strength for a typical rock, yield strength for typical rock is equal to 3 into 10 to the power 8 Newton per meter square. So this H rho G is equal to 3 into 10 to the power 8 Newton per meter square, or no need also. This unit is not necessary. Now, rho I am taking, rho is equal to 3 into 10 to the power 3 kilogram per meter cube. Then H is equal to 3 into 10 to the power 8 by rho into G, which is equal to 3 into 10 to the power 8 by 3 into 10 to the power 3, and G we will take 10. So this is how much? 5 here. This 3 and this 3 will get cancelled. So this is equal to 10 power 4 meter. 10 power 4 meter, which is equal to 10 into 10 to the power 3 meter, and that is nothing but 10 kilometer. So maximum height should be how much? 10 kilometer. But it is greater than Mount Everest, है ना? Mount Everest height is how much? 8.9 kilometer. Yes, this is practical value. That is this is theoretical value. That is practical value. So it is greater. It is greater than. It is greater than the highest mountain on the earth. On the earth. In bracket, Mount Everest, which is equal to how much? 8.9 kilometer, nearly 9 kilometer, है ना? So it is greater than that also. Understood? Note down. Okay, next, that is fourth one, pillars or columns. Pillars or columns. Okay, so see now I am drawing just two diagram. You will understand easily. This is the first one, and same pillar but distributed load. If you have seen metro pillars, you will understand this is distributed load. So these are more effective as compared with this pillar, right? So a with pillar with rounded ends supports less load than that with distributed one. Understand? Or distributed shape at the ends. Distributed shape at the ends. Right? Understood? No doubt. Right? Finished? Okay, next. Next one is bending of a beam. This is also applicative. New topic. Bending of beam. Bending of beam. So when we are giving load either at center or this side, at one side, then how we are getting this bending, that we are going to see now, right? So see, direct diagram I'm drawing. Suppose now like this plate is there, and it is fixed now at one end like this. It is fixed here, and now load is hanged at this end like this. And now this deflection is there like this. Okay, due to this load W, and this is, we can say, delta. Then then this delta is equal to WL cube divided by 3yi. 3yi, where I is the moment of inertia. I is the in system of particles we have learned when it is at one end or all these things. From that you have to calculate moment of inertia and you can use it, right? And suppose it is like this. I will give moment of inertia also, don't worry. And now here both side it is fixed, we can say, like this. And now load is applied somewhere here at the middle. Okay, load is applied somewhere here middle, and due to this rod is going to be like this. Here it is W, and this is what your delta is. Then in this case, delta is equal to WL cube divided by 48y into I. So already we have learned this backside, but this is in terms of y and I. There we have taken B and D also into consideration. So here moment of inertia for rectangular cross section, if like this is there, rectangular cross section, rectangular cross section, then I is equal to BD cube by 12, BD cube by 12, and here this is D and this is B. Next one, if circular is there, circular rod, then moment of inertia for this circular cross section, this is circular cross section, and for this I is equal to pi r4 by 4, pi r4 4 by 4, right? Note down. Yes, finished. Okay, next. So we'll stop here today.